Hello everyone. Our group project is personalized recommendation algorithm based on deep learning. The first part is introduction. Personalized recommendation is a key component of modern digital platforms. Our group provides personalized suggestion to user based on movie and user features from MovieLens dataset. We focus on combining traditional collaborative filtering method with neural network to uncover potential nonlinear relationships. Moreover, we compare them with traditional collaborative filtering methods to assess the quality of each model according to RMSE, precision, recall, and F1 score. The next part is dataset. The dataset contains a total of 4 CSV files, which is widely used in the research of the recommendation system. The left picture by randomly selecting 100 users and 500 movies. The matrix sparsity was calculated to be 0.5748. The results show that the interaction data is insufficient, and the existence of high sparsity makes it difficult for new users to get accurate recommendations. So we need to design a model to solve this kind of cold start problem. For the part of data processing, the first step is to load rating data and movie data. Filter out unpopular movies with rating below 20. The second step is to create an ID mapping, ensuring that the ID are continuous and adapted to the matrix factorization model. The third step is normalize the ratings. The fourth step is divide the dataset into layers based on timestamps. The next part is method. We explore 4 methods in this project. First is the matrix factorization, which is a traditional collaborative filtering model. It first obtains the corresponding embedding vectors from their respective embedding layers based on the indexes of user and movies. Secondly, it applies dropout to regularize the representation in order to prevent overfitting. Retrieves biased item to capture personalized features. Finally, the bias and dot product results are added to obtain the prediction results, which are mapped to 0 to 1 and iterated repeatedly until the model tends to be stable. Next is the neural collaborative filtering model. Due to the traditional collaborative filtering methods, the nonlinear relationship between the user and the movie cannot be captured. Therefore, on the bias of calculating the dot product of the embedding vector, the neural network is used to introduce the multilayer perception to learn the nonlinear relationship between the user and the movie. Next is the long short-term memory model. This model begins with 2 embedding layers that map user and item ID features into a 16 4-dimensional continuous vector space, addressing feature sparsity. The LSTM layer, with a hidden dimension of 128, captures long and short-term dependencies in user interaction sequence to model dynamic performance shifts. During prediction, LSTM outputs are concatenated with the current candidate items embedding and pass through a fully connected layer to generate a score. Next is the anti-graph-rag model proposed in this study. It starts from an embedding layer and maps user and items into a 16 4-dimensional space. Then, graph neural network layers, especially graph convolutional networks, capture structural information by propagating information between connected nodes. The attention mechanism is based on dynamical weighted representation of correlation, focusing on key features. Finally, the multilayer perceptron integrates this into the output prediction. The next part is comparison. This table compares the performance of MF, NCF, LSTM, and ATTEN-GraphRag models. From this table, we can find that the NCF has the best score in precision. which indicates that its neural network can better capture the relationship between user and movies. The high comprehensive score of MF indicates that it's suitable for sorting tasks. In this project, LSTM may be difficult to use its advantages due to the short time span of data. The worst training effects of a 10-graph rack may be due to sparse data and a few neighbor nodes. The next part is recommended results. The chart on the right shows the distribution of recommendations generated by the model. Although JAMA constitutes a large proportion in the dataset, as shown in the left chart, it only accounts for 19.4% in the recommendations results. This indicates that the model can effectively avoid over-recommending mainstream sorts. Now, let's explore how our model balances familiarity and novelty in genre recommendations. The left figure shows the distribution of genres. We find that 7 genres appear in user history and recommendations at the same time, while 3 genres only appear in user history and 2 genres only appear in recommendation. The right figure shows the performance of our model in terms of genre diversity. There are 10 genres in user history and 9 genres in recommendation results. Among them, 7 genres are common, indicating that the model retained the basic performance of users. Now, we see a clear demonstration of the model's recommendation logic. On the left, we have a user's historical high-rate films. This serves as the fundamental data points for our algorithm. On the right, you will notice the personalized recommendations generated by the model. This is the end of our presentation. Thank you.